So in this video, we're going to go over something called keto enol tautomerization. A tautomer is just a different version of a molecule. It's a constitutional isomer, and a tautomerization is just the doing of that, right? So it looks like a very scary word, but it's just the formation of a different version of some molecule. So in this case, the versions are a ketone and an enol. I'll go over what an enol is. Actually, I'll go over that right now. It'll make more sense. So an enol has two, parts to it, right? It has this ene and it has this ol. Well, the alcohol refers to an alcohol, right? Which we can see right here. And the ene refers to the ending of an alkene. Alkene, right? Alkene. So it's a double bond between two carbons and an alcohol, aka the ol. So it's pretty simple. You might not have heard it, but it's pretty simple. It's just this double bond and this alcohol right there. Okay. So first, we're going to go over one of two conditions: acid catalyzed and base catalyzed. So let's go over how to form an enol from a ketone. But keep in mind, there's a reason why I drew these double arrows right here in the middle. It's not as simple as you add some reagents to ketone and you make enols, because frankly, enols actually aren't that stable compared to ketones. So this is a two-way reaction. You might help it go to one direction, but in reality, this is a two-way reaction. If anything, is going more towards this direction because a ketone is more stable than an enol. Okay, an oxygen can carry a double bond much better than two carbons can. But nonetheless, let's go over the mechanism that produces these two, right? Which doesn't really matter which direction I go in. So let's go first from a ketone to an enol. I'm going to draw a ketone right here. Okay, and keep in mind that even if I have an acid in there like H3O+, these are almost always going to be in aqueous solutions, right? Aqueous solutions, meaning there's plenty of H2O to go around in these solutions. So that'll be important for later parts of this mechanism. So the first thing that's going to happen in an acid catalyzed reaction is going to be the donating of a proton, right? That's what acids do. Acids donate protons. So if I have these lone pairs on this oxygen, that's going to take one of these hydrogens and the bond is going to break and be taken to form a water. So our next step is going to be this. It's going to look like this, at least. We haven't broken this double bond yet, so we're going to have a positive charge, right? We have a formal charge of 5 right here. 1, 2, 3, 4, 5. So the next step after this is going to be the deprotonating of one of these alpha carbons, right? So these are considered alpha carbons right here. They're the first carbons from the carbonyl carbon, which is right here. So one carbon away from it would be the alpha carbon. If I had drawn, say, a methyl group attached to this, this would be a beta carbon right there. And there are no beta carbons here. And the subsequent hydrogens that are attached to alpha carbons right here are called alpha hydrogens. That's easy enough, right? Alpha hydrogens. So that'll be important terminology for later. So in this case, we're going to deprotonate one of the alpha carbons, right, by taking off one of the alpha hydrogens. Okay, so how are we going to do that? Well, we're going to use some sort of base. In this case, we're just going to use good old-fashioned water. In some classes, they'll accept, like for example, my class will accept a B-, right, where B- comes and takes this, and then this bond goes right here. So in this case, it doesn't really matter. You can use H2O or you can use B-. So it's going to take that hydrogen, and that bond between the hydrogen is going to form a double bond here, while at the exact same time, this double bond between the oxygen and the carbon, which isn't stable because we don't want a positive charge on that oxygen, and given that it's more electronegative, it's going to want to pull in those electrons towards itself. So that bond's going to break into the oxygen, and we're going to form this molecule, which is an enol, right? We have a bond between two carbons right here, and right here, and we now only have two hydrogens on this. There's also a third one here, by the way, but yeah, I didn't draw that. And of course, nothing happened on this left side, and now we have a enol. Okay, now let's do that exact same thing under basic conditions. And keep in mind, by the way, while this entire thing is in solution, right, this ketone and this enol, it's actually going this way as well. And like I said earlier, it's actually probably going more this way than it is going this way, right? So it's more favored in the ketone direction because ketones are more stable than our enols. See, this hydrogen's kind of acidic, it can let go of that, then you get a negative charge. It's actually much more stable to have it in the ketone version. But we of course observe both in the real world, so we're gonna go, that's what we're going over this, because we see both. Okay, so how about under basic conditions? Under basic conditions, it's a little bit simpler. It's a little bit simpler. The first thing that's gonna happen is a base. I'll go ahead and draw in these hydrogens again. And also, some of you might be wondering why I'm not, attacking this left side. Well, in this particular case, I just have two methyl groups. I just have two carbons that both have three hydrogens on them. So it doesn't really matter which one I attack. So in this case, when I have a base in solution, the first thing that's going to happen, instead of protonating that oxygen, is I'm going to steal one of these electrons, one of these hydrogens. Okay, I'm going to steal one of those hydrogens, and that bond's of course going to break and form this double bond. And what's going to happen if I do that? What's going to happen if I do that? I'm going to get. Do you ever see this in organic chemistry? I definitely don't. Right? This is a pentavalent carbon. You won't ever see that. So in reality, before we actually proceed to that step, we should also move this bond up. These two steps happen simultaneously. Okay? So this should look like that. And I'll go ahead and draw these hydrogens just to be safe. And then again, we do not want a charge on our atom because it's really, really not stable. I should draw this going in both directions. So we're going to draw the next step where a water comes in. And again, this is why I said it's very important to realize that these are always in aqueous solutions like they're on the left, because there's always water floating around, okay? So we can always use that as a base or an acid. So in this case, this negative oxygen is going to pull one proton off of that oxygen. It's going to act as an acid in this case. And we're going to form this molecule. Which is, again, exactly the same as this one over here. So we just formed another enol under basic conditions. So clearly forming an enol from a ketone is possible in both types of conditions, acid and base catalyzed.